Alright, so last time we looked at the definition of a limit, so I figured now we'll put that into practice and actually solve some limits. This first one is probably the easiest type of limit that you can do because it's obviously a continuous function. There's no holes, discontinuities, or anything, so really you could test what the limit would be by plugging in, values greater than 2 getting closer to 2, or smaller than 2 getting closer to 2, and see what they meet at as you approach 2. Or you could just plug in the value because we know it's continuous, so we know that the function has a value at x equals 2. And so for this one, we'll just plug in 2. So we'll have 2 squared plus 3. So the limit of x squared plus 3 as x approaches 2 is 7. Easy enough. Okay, but for this second one, we have a rational function with 2 quadratics, one in the numerator and the other in the denominator. And when you have a polynomial and you're trying to take the limit of especially a rational one, you want to factor them out because the limit might not be as obvious as it seems. So we'll factor these out. The factors of x squared plus 25 is x plus 5 and x minus 5. And the factors of x squared plus 2x minus 15 is x plus 5 and x minus 3. And so right here you can see that if we were to just plug in our value of x approaching -5, if x was -5 and we plug that in, we would get 0 here, because -5 plus 5 is 0, and a 0 here, so we would have 0 over 0. And that does not mean that the limit does not exist. Okay, but by factoring this out, we can also see that these x plus 5s, they cancel out because something over that same something is just 1. So it's ultimately just x minus 5 over x minus 3. So now we're at a point where we can plug in our value for our limit and not get 0. So let's do that. -5 minus 5 is minus 10. And minus 5 minus 3 is minus 8. So the limit as x approaches -5 of this rational function is 5 over 4. That's what the value of the function approaches as x approaches this value. That's what the function spits out as x gets closer and closer to -5. Okay? So now we have the third limit. The limit, we're using a different variable now, h, which some of you might recognize if you've taken calculus already. The limit as h approaches 0 of 6 plus h quantity squared minus 36 all divided by h. And if you were to plug in 0 here, you'd be dividing by 0, and that's infinity. That would not work out. So we need to make some changes to how we wrote out our function here. So let's FOIL this term out and see what we get. 6 plus h squared. 6 times 6 is 36. So we have 36. 6 times h plus 6 times h is 12h. Whoops, 12h. And h times h is h squared. H squared. And that's all minus 36 still. And that is over h. Okay, so right now you can see that the 36's will cancel, so that's good. 36 minus 36 is 0. And so we're just left with 12h plus h squared over h. And if we factor out an h, 12 plus h over h, well, something over that same something is 1. So that becomes 1, so it's just 12 plus h. So the limit, as h approaches 0 of this function here, is just going to be 12 plus our value that h is approaching, so 0. So it's just going to be 12. And this one will be connected in the next video to the definition of the derivative, which is based on limits. So, yeah.